Good afternoon, everyone, and welcome back to Virtual Thermodynamics. So in the last two videos that we're going to have on the topic, we're going to look at the last cycle we'll cover in our Introduction to Thermodynamics class, looking at vapor compression, refrigeration, and heat pumps. Now these cycles are essentially Rankine cycles in reverse, and instead of using them to generate power from heat, we're going to use work or power to sort of force heat to go in a direction that it otherwise wouldn't want to go. So because we're looking at refrigeration cycles, I think the logical question to ask is, do you want to build a snowman? So here's a schematic for a vapor compression heat pump, or really for a refrigeration cycle too, because they're almost the same thing. The difference will be what's the heat transfer component that we're interested in. In a heat pump, what we do is we create a machine where the hot side of the condenser is even hotter than the area that we want to heat up. So as I vent heat from my condenser, I'm heating up a hot room. In a refrigerator, we do the opposite, where we have a evaporator that's colder than the space that I want to keep cold, so that it accepts heat from the cold place, like inside my refrigerator or inside my house if I'm running my air conditioner. For a heat pump, what we're interested in is the heat transfer on the hot side. So that's our energy benefit. But if this was a refrigeration problem, we'd be interested in the heat transfer on the cold side, and we could do basically the same type of analysis. So to characterize our vapor compression heat pump cycle, we look at a coefficient of performance, or COP. You can use COP if you want. The Greek letter that we use for heat pumps is gamma, which is shown here. So this is our coefficient of performance. So if we're going to use this, then if we were doing a refrigeration cycle, we would use the Greek symbol beta. Like all of our characterizations, this will be the desired energy effect divided by the energy cost. But it looks a little bit different than it did for heat engines, because here our desired energy effect is heat transfer, in particular the heat that we're transferring on the hot side, and our energy cost is our net work. So if you've ever used a refrigerator, an air conditioner, or a heat pump, you have to plug them in because you're running some kind of a compressor, so they all consume power. In this case, our actual coefficient of performance is given by this equation, where we're looking at delta H over delta H, and we have particular states that are important. If we want to compare the coefficient of performance to the maximum potential coefficient of performance, we can use the Carnot coefficient of performance to find the maximum amount of heat transfer or of performance from a heat pump or a refrigeration cycle. Now, if you're curious why we're calling this a coefficient of performance instead of an efficiency, it's because coefficient of performance is generally greater than 1. So efficiencies always run between 0 and 1, or if you want to say 0 and 100%, that's okay too. But coefficient of performance are always, or at least most of the time, greater than 1. So you want to talk about these not in terms of efficiency, but in terms of a coefficient of performance. So the neat thing about these cycles is that we're making a machine that's kind of tricking the universe into transferring heat in a direction that it wouldn't normally want to go. So we're sort of pushing heat to the hot side from the cold side. And we do that by building a machine where one side is colder than the cold side, so it accepts heat from the cold side. And the other side is hotter than the hot side, so it rejects heat into the hot side. So one of the questions that you can ask yourself is T hot greater than or less than temperature of the condenser? Even though heat is being transferred on a macro scale from our cold area to our hot area, we make our device so that the condenser temperature is larger than T hot. So here T hot is less than the condenser temperature, and that's why heat is moving from our condenser to our hot space. Similarly, on the cold side, we make our device so that the evaporator is colder than the cold side so that heat is moving from T cold into the evaporator. That means that T cold has to be greater than the evaporator temperature. So like all of our cycles, we're going to ask what's the fluid and how do we find our enthalpies or the difference in our enthalpies. And there's several different ways to do this. So if you look at something like an FE handbook, you'll have a chart that we'll talk about that gives pressure as a function of enthalpy. You could look on the NIST website, which is linked here. You could look at refrigerant tables in your textbook. If you have a compressor, you know that delta H has to happen for the ideal compressor so that it's isentropic, or that S out is equal to S in. If you have a real compressor, then what you want is you want to look for the isentropic efficiency of the compressor. And in this case, we have a valve on the opposite side of the compressor, and we're always going to assume that that valve operates in an isenthalpic way, meaning that the enthalpy change across the valve is 0, or H in is equal to H out. So this is the type of graph that you might see if you were working on one of these refrigeration or heat pump type problems. This is a pressure versus enthalpy curve, in this case provided by DuPont and Suva for HFC 134A, which is a refrigerant. Now, this graph looks a little bit intimidating at first, but what we can remember is that this is a vapor dome. Now, essentially, these vapor compression, refrigeration, and heat pump cycles are Rankine cycles in reverse. So what they're doing is, on a plot like this, we're going to show how we get this two-phase mixture and when we're boiling it and when it's condensing. So a couple of things to note about these pH diagrams. The chart is pressure versus specific enthalpy, so that's what's on our main axes. We can get the most of the information we'd get from the tables on this chart. That's why it's so confusing, maybe why we have so many different lines, because we have lots of different properties that are shown on this table. The chart doesn't usually use the word specific when it's talking about different properties. For example, it will say enthalpy, but I think more specifically it means specific enthalpy. So the units will be in kilojoules per kilogram. This is true for lots of different properties. So if I'm looking at this pH diagram, it's important to know what it's telling me. So if I'm trying to read pressure, pressure is on my vertical axis. So pressure is constant on these horizontal lines, like the dashed lines that I'm showing here. If I'm trying to read enthalpy, I can read this vertically and bring it down to my horizontal axis, which is enthalpy in kilojoules per kilogram. I can try to find a constant temperature line, which if I just follow one of these constant temperature lines, I see that it comes down and then across, because as we're boiling, the temperature stays constant, and then it drops down again. So I might have to try to find a constant temperature line. If I'm looking for quality, quality only makes sense to talk about when I'm under the vapor dome. So here I look as I move from left to right. You can see quality, there's 0.2, 0.3, 0.5, 0.6. So I can measure the quality looking under the vapor dome. I can find specific entropy, which is, these are lines that are sort of, the slope of these lines is sort of changing. This is one of the more difficult things to read off this table, I find. And then I can find specific volume by looking at the lines like I'm showing here. So there's lots of different things to look on this graph, lots of different things that we can use to try to understand what's going on. So you might look at this and say, well, that's great that we have a chart, but how do we actually fix a state? So we have to remember that to fix a state at any time, what we need is two independent intensive properties. And if we have that, we can fix a state, and we feel like we can understand everything, or we could find out all the other independent intensive properties if we know two of them. So on this graph, each intensive property is a line on the graph. And if we have two independent intensive properties, Then we'll have two lines, and we'll look for the intersection between those two lines, and that will give us a point. That point denotes the state that we have on the graph. Once we have that state or that point, we can graphically estimate values for all the other properties that we're looking for. So now let's try a simple example. So here we have our 134A as our working fluid. It's moving between state 1 and state 2, and we're adding heat per mass flowing through our component. And we're asked to find little q dot, or q dot divided by m dot. We're told that state 1 has a pressure of 5 bar and a quality of 0.2, and state 2 has a pressure of 5 bar and a temperature of 20 degrees Celsius. Our control volume is going to be our component here. So the assumptions we're going to make, first we'll look at conservation of mass or continuity. We'll say that we're at steady state, that we have one inlet and one outlet, and that means that all the mass that comes in also goes out of my component. So I'm not storing mass inside my control volume. I can then do a first law analysis. We're at steady state. We'll assume one inlet and one outlet, that there's no change in kinetic or potential energy, that the system is passive, meaning that it doesn't consume or produce power, that there's no friction losses and no heat losses across my component. And when I do all that, I see that the heat transfer going into my component in this case is equal to m dot times h out minus h in, or h2 minus h1. I can then find a symbolic equation for q dot over m dot, which is what this problem asks me for. Unfortunately, I don't know q dot, I don't know h out, and I don't know h in. I also don't know the mass flow rate, but really I guess on the left-hand side, it's that I don't know little q dot, or q dot over m dot. So in order to find q dot over m dot, I've got to find my states. So if I can find h out and h in, then I can find my heat transfer per unit mass flowing through the system. So I've got some state information for state 1 and state 2, and I'm going to try to use that to fix my states. So let's find state 1. So the first thing I'm going to try to do is find a line where my pressure is 0.5 megapascals. So here we can see that the pressure is given in megapascals. So that's why I had to change it. This is a log scale, so I get 0.5 and 0.6, and I look for the line in between, and that's going to be 0.5 megapascals. The next thing I'm going to look for is the quality of 0.2. So I look on my graph down here, there's quality of 0.1, there's quality of 0.2. So I'll look for the intersection of these two lines, which is maybe a little bit easier once I highlight quality of 0.2. And then I can put my state point right there. So again, I know I've talked about this for a couple other problems, in particular for Rankine regeneration. If you're going to do an exam problem in thermodynamics, it's a good idea, in my opinion, to bring things like colored pencils. If you're looking to fix states on a graph like this, it might be nice if you're drawing your different lines in different colors. So what I actually am looking for is not just where the state is, but I want the specific enthalpy. So what I do is I take my point, I drop a vertical line down, and now I come down from here straight, and I can see where my enthalpy is. So I know that it's bigger than 250 and less than 300. If I had a ruler, I could sort of measure in millimeters where it's falling there, or I could just try to estimate something. And here I find that H1 is 260 kilojoules per kilogram. Now, this might be confusing if you try to do this problem in the textbook, because if you look in our textbook, you'll find that H1 is equal to 108.8 kilojoules per kilogram, and that's much different than 260. So this isn't just a graphical difference where I'm not reading the number off the table correctly. So why is the number different on the chart than it is in the table in my textbook? So the difference is that the textbook uses a different zero value for specific enthalpy than this chart does. So it's a little bit like the difference between, say, absolute pressure and atmospheric or in relative pressure or gauge pressure, or maybe the difference between absolute temperature and, say, a sensible temperature scale like Celsius, which uses 0 as the freezing point of water. But since both references give us values in kilojoules per kilogram, it's important to remember that they're offset. So it's a little bit different than temperature, where we have different scales denoting where the zeros are. And it's a little bit more like pressure, where gauge pressure and absolute pressure are both measured in kilopascals. So the textbook values are always about 150 kilojoules per kilogram lower than the values on these charts, which you can find in the FEA handbook. Our difference graphically was 151.2 kilojoules per kilogram, so we're doing a pretty good job here in estimating the value, but there's some error because we're reading our number graphically off the chart. So now I'm going to try to fix state 2. I have some state information, 2 independent intensive properties. So I'm still going to try to find 0.5 bar, which is given here, but now I want to find the temperature of 20 degrees. So here, if I look for this line that's 20 degrees, I see it hits the vapor dome, and then it starts to come across there just above my line for 0.5 megapascals, and then it's going to intersect past the vapor dome. So here my line is in green. My second state point is going to be somewhere around here. I'll drop my vertical line and I'll try to read the enthalpy, and it's going to be somewhere between 400 and 450. When I solved this graphically, I got about 412 kilojoules per kilogram, and the textbook told me it was 260.4 kilojoules per kilogram. So I can solve this problem with the textbook or with the table. In both cases, I have values for H in and H out, so I can find Q dot over M dot. If I use the information from the chart or from the FE handbook, it's the same thing. I get that Q dot over M dot is equal to 152 kilojoules per kilogram. And if I use my numbers from the textbook, even though they're offset by the same amount for H in and H out, so I get essentially the same answer. This makes sense because the answer that I get shouldn't be dependent on the method that I use to get it. So that's kind of an introduction to vapor compression heat pumps and refrigeration cycles, and an introduction to these pH diagrams. Thank you for joining me on Virtual Thermodynamics, and I'll see you again.